Hello everyone, welcome to the course on digital signal processing. This is lecture 1 and in this lecture we'll see the introduction of IIR filters. So first of all we'll see what are filters. So filters are basically the frequency selected devices. Now the certain frequencies which are passed and some frequencies which are attenuated or the frequency will be blocked. So based on that we can say the bands whatever we have called as the pass band and the stop band. So these pass band and stop band are corresponding to the filtered system function which is represented by h e raised to power j omega, where mod of h e raised to power j omega is a magnitude and phi of omega is called as the phase. Now the frequencies of a signal that are passed through the filter or the range of frequencies which are passed are called as pass band. Whereas those frequencies or the range of frequencies which are blocked by this filter is called as stop band. Now, the frequency in the pass band, the magnitude or the amplitude of h e raised to power j omega is relatively large. Means the magnitude of h e raised to power j omega is very high, large in case of pass band, whereas it is very low in case of the stop band. So a stop band is characterized by the magnitude of the frequency response h raised to power j omega which is relatively small, and ideally we'll see later on that what is for a ideal filter, the stop band, the gain in the stop band is nearly equal to 0 ideally, or else it is very small. Now we have two frequency response over here. First, in the first figure we have the magnitude response of a low pass, practical low pass filter, this dark solid line, and we have an ideal frequency response of a low pass filter which is here shown in the dashed lines. Now this omega c is a cutoff frequency. Now the cutoff frequency is basically, as per the definition, the cutoff frequency or that particular frequency where the gain reduced to the 1 by root 2 times the maximum gain. Now whatever the frequencies which are less than the cutoff frequency, so those frequencies are basically the pass band frequencies which are to the left side of omega c, whereas the frequencies which are blocked, which are greater than omega c, they will be blocked, and this particular band is called as stop band, and the frequency omega c is called as the cutoff frequency of the filter. Now we have the typical Butterworth response. Later on in our classes we will see that the IIR filter, the types of IIR filter, we have two types of IIR filters. First is the Butterworth kind of response or the Butterworth filter, and the second one is called as a Chebyshev filter. Now again we have the magnitude response over here for the ideal low pass filter and for a practical. This is the ideal and this one is for practical filter. So this shaded portion, this is called as a attenuation. It is called as a attenuation in pass band. Whereas in the stop band, the attenuation is given by, let's say, A2. So this is called as attenuation in the stop band. So as per the specification, if we talk about the specification of the filter, so we have certain specifications which are the attenuation in pass band, the attenuation in stop band. Also in the frequency we have the pass band frequency and we have the stop band frequency, and between these pass band and the stop band frequency we have a band which is called as transition band, which is called as transition band. Later on we will see that as the filter order increases, the width of the transition band decreases, means the frequency response or the magnitude response of a practical low pass filter will attain a similar kind of response as we are getting for a ideal low pass filter. Means as order improves, order increases, the filter becomes ideal. Now we have the types of filters. So the filters are classified on the basis of their impulse response, as we have FIR and IIR. So first of all, we will see the type of filter which make use of feedback connections. Means if there is some feedback, some part of the output is again feeding back to the input side, those type of filters are called as recursive filters, and the impulse response of these type of filters are of infinite duration. So that's why these type of filter are called as infinite impulse response filter, IIR filters. Whereas the type of filters which do not employ any kind of feedback, and they are called as non-recursive. If there is no feedback, it is called as non-recursive filters, and the impulse response of these type of filters are having a finite duration. So that's why these filters are called as finite impulse response filters. So these are the differences also between the FIR filters and the IIR filters. So these IIR filters are designed by considering all the infinite samples of the concerned impulse response. Now the impulse response is obtained. How can we obtain the impulse response? Let's say we are using the Fourier transform. So I have to use the inverse Fourier transform. We'll be applying the inverse Fourier transform of a ideal frequency response, and we are getting a impulse response of the filter. Now there are several techniques for the designing of filters, digital filters having a infinite duration. Means we are talking about the infinite impulse response filter. So there are certain popular methods which are used for such filters, and the technique used for these type of filter, digital filter design, is that first we'll design a filter in analog domain. We'll design an analog domain filter, and then we'll transform this analog domain filter into a digital domain with the help of transformation technique, which is called as analog to digital frequency transformation. So this analog domain filter is then converted into the corresponding or the equivalent digital filter, because the analog filter design techniques are well developed basically. So later on we'll discuss various methods for transforming an analog filter into a digital filters, and we'll see the method of designing a digital filters. So this is the basic theme behind the design of IIR filter. So first we'll design an analog filter, and then we'll transform to a digital domain or the digital filter. We have a basic comparison over here, that first of all this FIR stands for finite impulse response filter, whereas IIR stands for infinite impulse response filter. Next we have the nature. As we are already aware that FIR filters does not having any kind of feedback. This means the feedback is absent. So as the feedback is not there in case of FIR, so these filters are called as non-recursive filters. As a counterpart, we can see that the IIR filters are having a feedback. So on the basis of that, we can say that the IIR filters are recursive. Now as a stability point of view, since in the transfer function or the system function of FIR filter, we generally have the unity in the denominator. So we generally filters are inherently more stable in comparison with the IIR filters, because in IIR filters we'll be having the poles, and on the of poles we can comment upon the stability. So in general we can say that the FIR filters are more stable in comparison with the IIR filters. Now as the definition of the recursive and non-recursive. So first of all, FIR filters means the present output depends only on the present or past inputs. If this is a scenario, This is called as non-recursive. Whereas in IIR, the present output depends on present input, past input as well as past output. This is the only difference. On the basis of the transfer function, we can say that FIR filters are having, it's a only zero function, only zeros are present in the system function of FIR. Whereas in case of IIR, we have both poles and zeros. Last point regarding that FIR filters are having a linear phase. That's why we have a linear phase representation also for a FIR filter. Whereas the IIR filters are having a, they don't have the linear phase, and we cannot achieve the linear phase in case of IIR filter. So these are certain comparison between the FIR filters and the IIR filters. Requirement, what is the need of transformation from an analog filter to digital filter? So first of all, let's say we'll have the transfer function of an analog filter. Later on we'll talk about a prototype analog low pass filter. So we have the transfer function HS with this A as a variable. So A is nothing but the analog filter, and it is nothing but the ratio of Laplace transform output Ys to the Laplace transform input, which is Xs. This is something in this particular form. We have summation k equal to 0 to m. Bk are the coefficients, IR filter coefficients, s to the power k whole divided by k equal to 0 to n ak s to the power k, where these ak and bk are called as a IR filter. The impulse response of these filter coefficient, it can also be associated with the help of the Laplace equation, which is h of s is equal to the integration part minus infinite to infinite ht e raised to the power minus st dt. So this is our second equation. Now if we'll use our first equation and we'll cross multiply like this, so we'll be having ys summation k equal to 0 to n ak s to the power k ys. Now we have a property which is d by dt of xt, the Laplace transform will be s times of xs. If we have d nth times of xt, we have s is to the power n x of s. The property is called as the differentiation in time domain. So on the basis of that, if we cross multiply our equation number 1, and we are getting this summation k equal to 0 to n ak and the kth derivative of yt equal to the summation k equal to 0 to m bk and the kth derivative of xt, where again xt and yt are the signals. Xt is the input signal and yt is the output signal of a filter, and the filter is represented by its impulse response ht. So on the basis of these three equations, equation number 1, 2 and 3, we have three different methods. So the above three equations, equivalent characterization of an analog filter leads to three different alternative methods for transforming the analog filter into the digital filter. So on the basis of these three equations, we'll be having three different methods. Later on we'll see in our lecture. Now what are the restrictions on designing? So the restriction on the design is that the filter should be realizable. It should be realizable as well as stable. Realizable means the filter must be causal. So if the system is causal, then it must be physically realizable. If it is non-causal, we cannot realize. So the restriction is that first it must be realizable as well as the filter must be stable. If the filter is unstable, so it's again of no use. Now we have for a stable and causality of an analog filter. So we are already aware that in S domain, how we can check the stability. this is in S domain and this one is in Z domain. So in S domain, we can say that HA of S, this one, the transfer function, should be a rational function of S and the coefficient of S should be real. This is the first point. Next is, on the basis of location of poles, we can say that the poles of this H of S must lie in the left hand side of S plane. Again, it's a condition for the stability because we have already a causal system over here, and if we can say that the poles are lying in left hand side of S plane, so we can understand something like this. If we have sigma, this is J ohm, this is S plane, and if you are saying that poles are lying in left hand side of S plane, so the ROC will be something like this because the system is causal also. Causal means right side. The ROC will be right to the rightmost pole. So definitely this ROC contains the unit circle. So once the unit circle is contained, then we can say that the system is stable. So this much of information we are already aware in signal and system. Also, the third important point over here is that the number of zeros, definitely in the numerator, the order, the power in the numerator is definitely less than the power in the denominator. Means the number of zeros should be less than or equal to, the marginal gain is equal to the number of poles present in the transfer function H of S. Now this is regarding the stability of an analog filter. Now the stability of a digital filter. So the digital filter can be represented by the system function H of Z, and again the same point is applicable to here also, that Sz must be a rational and the coefficient of Z must be a real quantity. It should be a real quantity. Similarly, if we talk about the complex Z plane, which is something like this, it's a unit circle, and if the poles are lying inside, so the ROC will be outside the outermost pole, and again definitely in this ROC the unit circle is contained. Once the unit circle is contained, that means we can say that the system is stable because it is causal also. Causal means the ROC is right to the rightmost pole. So the poles must be lie inside the unit circle. Apart from that, the third point will be the number of zeros must be less than or equal to the number of poles present in H of Z. So these are the key points behind the analog filter as well as the digital filter. Now, the analog filter with transfer function H of S is stable. We are already aware that if the poles are lying in the left hand side of S plane. Consequently, for the conversion technique means if we are converting a S domain or an analog filter into Z domain, which is digital. So consequently, for the conversion technique to be effective, it should possess the following desired properties. The first point, the imaginary axis in the S plane should be mapped onto the unit circle in Z plane, and the mapping, and there will be a direct relationship between the two frequency variables. Later on we'll see in analog domain we have an analog frequency represented by ohm, and in digital domain the frequency is represented by W, or we can say this is omega. So there must be a direct relationship between the two frequency variables in the two domain, S domain as well as Z domain. Also, the left hand side of S plane should be mapped inside the unit circle, and a stable analog filter will be converted and the stable analog filter that is in S domain is converted into a stable digital filter in Z domain. This stable filter in Z domain. So these are the few points again associated if we are using the transformation, if we are moving from analog domain to digital domain. So these are the desirable properties. The filter must be having these properties. Now we have the mapping. This is quite important. To the left, we have the S plane, and to the right, we have the Z plane. Now, the mapping part, later on we'll see that Z equals to e raised to power S T, capital T. Now, S equals to sigma plus J ohm, whereas Z equals to R e raised to power J omega. So now when sigma equal to 0, if you put in this one by substituting S equal to sigma plus J omega, we can say that the imaginary axis in the analog domain is mapped onto the unit circle in Z domain. This is the first point. Next is the left hand side of S plane is mapped inside the unit circle. It's inside the unit circle. The right hand side of S plane is mapped outside the unit circle. This is outside the unit circle. That means if the analog filter transfer function is having certain poles lying in left hand side of S plane, so automatically during the transformation to Z domain, the digital filter is having a poles which will definitely be lying inside the unit circle. That means a stable analog filter definitely results in a stable digital filter. So these are the key points again. Now, yeah, we have a comparison here between the analog filter and the digital filters. First of all, digital filter, it operates on the digital samples. Later on, we'll be seeing that whenever we are converting this analog domain filter into digital domain, so we'll be using the technique called as sampling. So accordingly, we have the sampled or the sampling frequency we'll take, and accordingly, we'll be having a sample time Ts. So it operates on the digital samples. Here, it operates on analog signals or the real-time signals, actual signals. Next point, digital filter, it is governed by the linear difference equation. What is the difference equation? Something like this: Yn equals to some B naught times of Yn minus 1 because it is recursive, plus A naught plus, or we can have A naught times of Xn plus A1 times of Xn minus 1, something like that. This is called as a difference equation. Whereas in IIR, it is governed by the differential equation. We have, let's say, d2y by dt square plus some A times of dy by dt. Again, to the right, we have some xt and derivative of xt. In digital filters, the basic building block of a digital filters are the adder, the multiplier or the gain elements, or the third is the delay element. So we have the adder, multiplier and the delay elements. So these are required for the implementation of digital filters, either in hardware or software or both form. Whereas the analog filters, it required the resistors, capacitors and inductors for the realization. Now in digital filters, the filter coefficients are designed to satisfy the desired frequency response. Whatever the frequency response we have, it will be represented by e raised to power j omega, because it is the frequency response of digital filter. And in the analog filter, the approximation problem is solved to satisfy the desired frequency response, which is given by h of omega or h of j omega. So these are the key differences between the analog filter and the digital filter. Now the advantage part. What are the advantages of digital filter over analog filters? In analog filter, the value of resistors, capacitors and the inductor used, they get changed with temperature, and the digital filters do not have these components. So we can say that the digital filters are having high thermal stability in comparison with their analog filter counterpart. In digital filter, the precision or the accuracy depends on the length, the bit size of the resistor, whatever we are using to store the filter coefficients. So as the length of the length or the size of the resistor get increased, the accuracy, the precision of the respective filter get improved, means we can increase the performance. Whereas next is the digital filters are programmable, because these filter coefficients are stored somewhere in memory. So we can program these digital filters easily. Hence the digital filter coefficients can be changed anytime to implement the adaptive features. But as we will see in the analog filters, we'll have the values capacitor, inductor, resistors, and they are not adaptive, right? So the values are fixed. A single filter can be used to process multiple signals by use of a multiplexing techniques. In the digital filters, in the digital signals, we have the multiplexing techniques, so we can utilize those multiplexing techniques to process multiple signals at the same time. But we don't have the flexibility of this multiplexing type of flexibility is there in case of analog filters. So that is also a main advantage of digital filter. Now the the coin is having a two side, one is head, one tail. Likewise, we have the disadvantage also for our digital filter, the bandwidth. The bandwidth of the digital signal is limited by the sampling frequency. Sampling frequency is quite important. So the bandwidth is limited by the sampling frequency, because the bandwidth of the signal is nothing but FM, or it will be FM is Fs by 2. So the bandwidth of the real discrete signal is half the sample frequency. And the performance of the digital filter depends upon the hardware, that is depend upon the bit length of the resistors. Whatever we have the length of the filter, so the performance is depending upon the bit length of the resistors in the hardware. So it is again used to implement the filter. So these are the certain drawback we can say, that the length of the filter is again by achieving a very high length of the filter, we can definitely achieve a high accuracy. By the same time, the filter will get more complex and the cost will be too high. Now we in short will see what are the important features of the infinite impulse response filter. First is, it is physically realizable, and the stable IIR filter cannot have a linear phase. It cannot have a linear phase, as we can see in case of FIR. For a filter to have a linear phase, the condition, which is h of n equals to h of m minus 1 minus n, and the filter would have a mirror image poles outside the unit circle for every poles inside the unit circle. So that will result in an unstable filter. It will result in an unstable filter because of the mirror image poles which are outside. So if the poles are outside the unit circle, let's say in Z domain, if the poles are lying outside, so that means it is nothing but an unstable type of a filter. So as a result, a causal and stable IIR filter cannot have a it cannot have a linear phase. That's why IIR filters are not having a linear phase, whereas FIR filters are having a linear phase. In the design of IIR filters, only the desired magnitude response is specified and the phase response is obtained from the designed methodology is also accepted. So these are certain key features of the IIR filters, and later on in our next lecture we will see what are the various techniques to design a IIR filter. So the methods are approximation of derivative, impulse impedance transformation technique, bilinear transformation. So in the next lecture we will see these techniques. Yeah, these are the references. Thank you.